ये लाइट बंद हो सकती है? Yes, लाइट हो सकती
यार वो हो नहीं रहा है यार।
सर को प्रॉब्लम आ रहा है। नेक्स्ट टाइम आज वाली
Okay, thank you. Don't worry about the version. You know, the options are similar. You just need to find them. They are, you know, placed at a different location in the new version. But I strongly recommend that you should get the new version. Okay. Okay, let's get started. In our previous class, yes, please pay attention at the back. In our previous class, we covered some of the draw and select menu, and briefly I think view menu.
Yes, sir.
Today I shall cover the define menu and assign menu. Okay, define menu is most frequently used menu in the software. So I will create a new file again instead of using the previous one. Let's go over the procedure as well. So I will choose a structure which has 5 grid lines in both the directions, and it has a grid spacing. I will just use the typical grid spacing instead of using multiple. Let's make all the grids 15 feet, and let's make it 1 story and 12 feet high. That's fine, or make it 15 feet. Okay, and have grids only. Press OK. So we'll end up with a single story grid line. Okay. Now I will go ahead and save it. That's the first step you should always do. Where is that, gentlemen? Desktop? ETABS? Okay. Okay. And I shall also go ahead and quickly plot the sections. Okay, let's not plot the sections. Is that door open?
Yes.
Keep that one open. Okay, so I'll go to define. You can note down what we have to define here. Number 1, we have to define material properties. Material properties means it is made up of concrete and steel. RCC. We have to decide the the strength of the concrete. We have to define, and also the Fy or yield strength of the reinforcing bars. That's what we have to define. Then we have to define frame section. Second thing is frame section. ETABS call the line elements as frame. It can be a beam, it can be a column, it can be a member of truss. Anything which is a line element is a frame in the language of ETABS. Okay, so we'll define frame sections, and then we shall define slab. Okay, so you can define here in the third menu, in the third option, wall / slab / deck section. Wall is for shear wall. You know, I told you about lift well or shear walls to restrict the lateral movement. So you can define walls, or you can also define retaining walls. You will study after the midterm in this course the design of retaining wall. You can define retaining walls here, but right now we shall define the slab. Okay, Then we shall define static load cases. In the newer version, you shall see an option of load patterns. Okay. There is also an option of load cases, but that is different. So in older version you define load cases, and in new version load pattern. Cases or pattern mean dead load, live load, earthquake load, wind load. I mean defining what types of loads the structure can be subjected to potentially. That's very important. Okay, static load cases or load patterns. In the new version, you will also find an option of load cases. Anybody has new version here?
Yes, sir.
See, in the new version, there are two options: load patterns and load cases.
Yes.
Okay. You will use the option of load pattern. Okay. In new version, load cases means that's an additional feature of new version, that you may have defined several loads, live load, dead load, earthquake, wind, and all that. If you want to run the analysis only for one load pattern, for example, you say, okay, I just want to right now analyze my structure for earthquake, although you have defined all in patterns. So you can go to cases and switch on or switch off the loads for which you want to analyze the structure. This facility is not in the older version. So you can go to load cases and say, okay, only run analysis for earthquake, and the remaining you switch off. So that will save your time. But in the older version, you don't have that facility. Then the next one, after load cases, we shall use load combinations. Load combinations. You are familiar with ACI load combinations. 1.4 dead, then 1.2, no, 1.4 dead is first load combination. It's not actually a combination, but it's a factor. If you open up ACI code, you will find 1.4 dead is number one. Second is 1.2 dead plus 1.69, and maybe something on the roof. And there are several which involve earthquake as well as wind. I will show you this week. We shall finish this ETABS, and next week we shall talk about some code and other things. So I will show you there. But ETABS also has it in its library, which you can see. So these four options we are going to use. And also there is another option just below load combination which says add default combinations. You find it?
Yes, sir.
Add default combinations. Okay, in the newer version, do you have special seismic load effects. Special seismic load effect. Right now we shall skip this special seismic load effects because you have not studied earthquake loading. You shall study earthquake loading in structural engineering. Okay. UBC 97 or IBC 2000. UBC is Uniform Building Code, and IBC is a newer version of that code, which is International Building Code, prepared by International Code Council (ICC). They gives you guideline for the calculation of earthquake load. Okay, because right now you have not studied earthquake loading, that's why I shall skip this. But you have to use it in future. Special seismic load effect, and the last option, mass source. Do you have it? Okay. It's there in new version, but maybe displaced. So these two options, special seismic load effect and mass source, are related to earthquake loading. Okay. So we shall use them. Maybe at later stage we can have a session and we can go ahead and use it. Okay, let's first come to material properties. Everybody has a laptop, right? At least one laptop in one row. Is there anyone who has no laptop? Everybody has it. Okay. You have the power back? Okay, very good. Go to material properties. Okay, how long will it take? Oh, okay, good. It's back.
Single line member frame, okay?
Yes. Line member?
Single line.
No, actually it's a term of ETABS designation, not the frame in terms of structural analysis. No. It's just a name. Okay, you go to define, you go to material properties. When you click on material properties, you see something like this. You see by default there is concrete, CONC is concrete, others, and steel. Okay. Our building is made up of concrete, so we have two choices. One choice is either we use this one and modify its properties according to our need, or we add a new material. Okay, let's go easier way. Pick this up, concrete, and go to modify, show material. When you open this up, okay, you need to know what is the strength of your concrete. The regular concrete which we use is 3000 psi compressive strength or 21 megapascal. Okay, right now this is in kips and inches. Be aware the units at the bottom. Look at the units at the bottom. In the older version, you have units at the bottom. In the new version, you may change the units and you click there and there is a panel and say, okay, which units you want to choose. But right now my units are in kips and inches. So 3000 psi is actually 3 KSI. Okay.
How many KSI?
3. Let me go to Notepad. How can I go to Notepad? Oh, search. FC prime equals to 3000 psi, which is equal to 3 ksi, okay, which is equal to 21 megapascal, right? So we are using FPS systems of unit. So my units here are kips and inches. KSI is actually kip per inch square. Okay, 1 kip is equal to 1000 pounds, right? So I will go to the software. The first thing you should do is have a name, and always have a meaningful name. You can call it concrete 3000 or concrete 3, so that when you look at the name you can understand what is inside. Okay, concrete 3000 means it's a 3000 psi compressive strength concrete, but merely by giving it name 3000 doesn't make it a 3000 psi strength concrete, right? You have to define it in its property right here. Specified concrete compressive strength. Because my units are kips and inch, so I will write here 3. And then bending reinforcement yield strength and shear reinforcement yield strength. What is bending reinforcement? It's the longitudinal reinforcement in a beam or in a column. And what is shear reinforcement? Stirrups. In most of the cases we use same strength, but in some cases people use 60 KSI for longitudinal steel and 40 KSI for the stirrups, but we will keep the same for both of them. So I will leave it unchanged as 60 KSI. Okay, that is the yield strength. Then do not change mass per unit volume, weight per unit volume. These values are correct by default. You can change this modulus of elasticity only. Modulus of elasticity, you remember the formula? Okay, for FPS units it's different, and for SI units is different. What you are telling me is in SI units that is 47,000 under root FC prime. This is for SI units. For FPS unit it is 57,000 under root FC prime. Okay, and this FC prime is in megapascal, and this FC prime is in ASI. Always remember that here you have in PSI. So you will plug 3000.
So what's that in FPM?
57,000 under root 3000. Can somebody give me the answer? 57,000 under root 3000. I forgot to bring my whiteboard marker. Yes. 57,000 under root 3000. Yes. 312218.5. This is PSI. Remember that FC prime and modulus of elasticity both have same units of stress. Okay. This is in PSI. We have to plug the value in KSI. So we divide it by 1000. So that will become 3122 KSI. 3122 KSI. So instead of 3600, actually 3600 is for 4000 PSI concrete. So I will change it to 3122. Rest is fine. Poisson's ratio is 0.2 for concrete. Don't have to change. Other things, let's leave them like that. Okay. So when you do this, and because you are defining in KSI, so maybe I can change the name to concrete 3. Concrete 3 means concrete with 3 KSI compressive strength. Okay, I press OK. So you have not just defined concrete, you have defined RCC. You have told that concrete is 3000 psi, okay, and steel is 60 KSI yield strength. So you have defined concrete and steel together. Press OK, and you will have this concrete 3000 in your library. So for now, the material which we wanted to use has been defined. Now the next thing which we need to define is frame section. Okay, I repeat myself here that ETABS calls every line element as a frame. Do not confuse this word frame from the frames you have been solving in structural analysis course. Okay, in that case the frame is a portal frame or a cable frame combination of beam and column. That is different. This is the language of ETABS. Every line element in ETABS is called a frame. Beam is a frame element, column is a frame element, any truss member is a frame element, anything which is line. So in our case, we have two types of frames to define. One is beam and the other is column. Now the question is that at the beginning, when you are designing the structure, you are not sure about the sizes of beams and columns, which means that you need to do some approximation, or you need to use some guidelines which tell you some tentative sizes. And most of the time, the sizes we begin with are based on deflection criteria. Maybe in PRC1, when you were designing beams, you learned about this, that maybe L by 16 or something like that. For example, if you forget every formula, then the simplest formula for guessing the size is L by 12. Okay, and even simpler is that number of feet. For example, it's a 30 feet span, then you can have a 30-inch deep beam. 12 feet span, beam is 12 inches. 30 feet, 30 inches. 24 feet span, 24 inches beam. Okay, if it is 25 feet span, then you have beam of 25. But instead of 25, you can round it off to 3 inch. So either make it 24 inch or make it 27 inch. And this includes the depth of the slab. When I say a 24 inch deep beam, it doesn't mean that the drop of the beam is 24 inch. It means that this drop of the beam plus the slab thickness is 24 inches. So from the top of the slab to the soffit of the beam, the bottom is total depth of the slab. Okay. So if you want to model this thing and you don't know the size in the beginning, I would say, okay, it is a 30 feet span, you can begin with 30 inches. Okay. Now about the width, this is depth, about the width. Generally, there is a practice among engineers, there may be some exceptions, but generally we start from 12 inches and then round it off to next 3 inches, maybe 12 inches, 15 inches, 18 inches, but 12 inches is or 15 inches is a very reasonable number when it comes to real life practice. You can make it too small, but nobody goes below 9 inches. Sometimes there is a requirement from client that we want all the beams 9 inches wide. Why? Because if there is a wall which is 9 inches thick, then there is a beam which is 9 inches thick, so beam and wall are flush. Otherwise, if beam is 12 inches, wall is 9 inches, there will be a cut. You will see a 3-inch projected portion of the beam. So that's why sometimes clients say, okay, we want 9-inch wide beam. So you have to think, and I'll take you back to PRC1. In 9-inch wide beam, you can accommodate hardly 3 steel bars. You have to maintain a distance between the steel bars. so that the aggregates would pass. So these things are important for us. So in no case you go below 9 inches, but 12 inches is a very good, is a very decent number to start. Right now, our spans were 15 feet. Okay, so I can define some beams 9 inches wide or 12 inches wide by 15 inches deep, or maybe 18 inches deep. This is the minimum requirement for deflection. The formulas in ACI for the spans of the beams are the minimum requirements. You have to go sometime beyond that. Okay. So I will define my beams as say I define two sizes, 9 inches by 15 inches and 12 inches, or maybe 9 inches by 18 inches, or 12 inches by 15 inches, and 12 inches by 18 inches. You can define as many beams you want to define, as many as you want. It is better to define more options, because when you design it in the end, maybe 9 by 15 is not satisfying. So you can go ahead and pick the other one. You don't have to define it again. So you can define ample number of sizes so that you can play with those sizes. For the same span, sometimes you need different size, because, for example, if you look at this beam has no wall on top of it, right? But this beam, which you can't see, it's flush with the wall. The beam here has a wall of S4A on top of it. So beam which has wall on top of it may be of bigger size as compared to the other beam with no wall, and both having the same span length, right? So you need different sizes. Okay, so I will define these 915, 918, 1215 and 1218. So I will go to define menu and go to frame sections, and here you will see already a long list of sections. Actually these sections are steel sections. You have seen table of sections in your steel manual. Actually these are those sections, and all those tables are in the library of ETABS. So if you are designing a steel structure, then you can use this library. You don't have to actually define those steel sections. But right now we are sticking to concrete. That's why I will simply select all of them and delete them. Select them and delete them. You can't delete the last one, so you will have to live with this. Okay, right here our beams are rectangular beams. Okay, so I will come here and pick up this, add rectangular. Don't worry about deleting. Okay, let's define it. I just deleted it because I didn't want to see them here, but there is no other purpose. Go to add rectangular. We are trying to define our beam. So you pick add rectangular and this message box appear. So first of all, name, and I said your name should be meaningful names. So I will call this beam BM 9 by 15. Okay, what is the material of this beam? Which concrete? Of course reinforced concrete, but it is not reinforced concrete. Yes, it is 3000 psi. So somewhere I should have that 3000 which I have already defined, right? And it is right here in the small panel in the material drop down. you will see that my concrete 3 is already in the list, right? So you can pick from here the material you have already defined in your previous option. So pick concrete, and right here you will put the sizes. Depth is 15 inches and width is 9 inches. Okay, 9 by 15. Okay, then you will go to reinforcement. You will go to reinforcement and tell the software that this is not a column, this is a beam. This radio button is a beam. Okay, right here is concrete cover to rebar center. Concrete cover to rebar center. What is concrete cover to rebar center? What do we call it? We call it effective cover. From the face of the concrete to the
Center of the
rebar. Effective cover. Right. Can somebody get the marker? I want to draw it. One thing is called clear cover. Right? Clear cover is from the face of the concrete to the edge of the steel bar. Right? But we are talking here about the effective cover to the center of the rebar. Okay. What is generally the cover for beams?
40.
Okay, look at this. You have concrete surface, the soffit of the beam, and then you have shear reinforcement, and then you have steel bar, longitudinal steel bar. What this is talking about is from the center of the rebar, this distance, which is equal to what? Is equal to clear cover plus dia of shear steel plus half dia of yes clear cover plus dia of stirrup plus the diameter of the half the diameter of the longitudinal bar. So it means you need to know what is the size of the longitudinal bar. Generally, this steel, shear steel, is commonly number 10. Number 16.
6
Is number 10. Is number 10 or number 3. This is SI and this is FPS. In FPS it is number 3 and in SI it is number 10. Actually there are 3 different sizes designation. One is US customary, which is this one number 3, number 4. The other one is in SI and there is another one which is American units, but it is in metric system. metering. There's small difference between them. But I think you learned this number 10. After number 10, you have number 13, I think.
Yes, sir.
And this one, longitudinal bar, has variation. Longitudinal bar in the beams is generally either number 13 or what's the next one? Number 16. Number 16. Up to 25. Up to number 20. Generally, we don't go beyond number 25 in case of beams. Okay. So what you need to do here is you need to review these sizes. Review sizes of steel bars, both SI and FPS. In our field, I think 99% is FPS steel bar system.
Yes.
Right? So we do a lot of testing in our labs. And once in a blue moon, we have a steel bar which is in SI system. Very rare. All the time we do FPS. Okay. So you need to be familiar with the FPS designation of steel bars. Okay. Which is number 3, number 4, number 5 is simpler. Number 6, number 7, number 8, number 9, number 10. Generally, the common sizes are in Pakistan, number 3, number 4, number 6, and number 8. These 4 sizes are very common. Okay, and easily available in the market. If you want number 5 bar, then you have to specially place an order, and then we manufacture number 5 bars. You don't generally find. In Pakistan, generally we have even number of bar sizes available. Okay, so we rely on number 4, 6, and 8 for longitudinal reinforcement, and number 3 for the rings. But in case of bridges, where you have huge sizes, we may have number 4 as a shear reinforcement as well. Okay, but generally number 3 is enough for regular buildings. So you need to remember their sizes and their corresponding areas. Okay, for both of them. Sorry. For shear, generally number 3, and for longitudinal, number 4, 6, and 8 is common. And this designation, number 3 or number 4, what does that mean?
3 by
This is actually
inch.
3 by
the diameter is 3 by 8 inch. The diameter is 4 by 8 inch, 5 by 8 inch, 6 by 8 inch, 7 by 8 inch, and 8 by 8 inch, which is of course 1 inch. This is 1 inch, and this is half inch. Okay, so no matter what units designers are using for their real design, but the bar sizes are used in FPS units. Sometimes you will see that drawings are prepared in SI units, millimeters and meters, but the bar sizes are still the FPS bar sizes. So you need to be familiar with these sizes. I will show you a table. You may have it in your concrete book by Dr. Zaid Siddiqui, a table at the end which shows all the bar sizes for different destinations. So this effective cover is clear cover. Now this clear cover is also provided by ACI code. That what should be clear cover for a normal environment. For sphere weather it may be different, for interior it is different, for exterior it is different. For something exposed to the soil, it is different. If it is exposed to the water, for example, in a swimming pool, it is different. Underground basement, it is different. So there is a guideline. Anyhow, generally, this may be, as you said before, for example, if this is, say, if I talk in terms of inches, if this is 1.5 inch or 1 inch maybe, then shear reinforcement, what is the diameter? 3 by 8 inches. Okay, so clear cover, say it is 1 inch plus 3 by 8 inch diameter of steel, and then this longitudinal bar, say it is number 6 bar. So number 6 bar, what is the diameter? 6 by 8, which is 0.75 inch. Okay, so plus 1 by 2 of 6 by 8, number 6 bar. This is number 6, this is number 3. So can you quickly do the math and tell me what is the answer? This cover
1.7.
is maybe 1 inch to 1.5 inch, but I am just taking it 1 inch. 1.87.
1.75.
Okay, so we were defining our beam and we said that it's a beam, and the cover in inches to the top bar, how much? 1.75. 1.75. Okay, are you sure about this?
Yes.
Okay,
Yes, sir.
1.75 inch. If you make it the clear cover 1.5 inch, then this value will be 2.25 inch. Okay, just leave this bottom option, you are not concerned with this right now. Press OK. So once you do this, then you can say that your beam has been defined. One beam size 9 inches by 15 inches has been defined. You have to define 4 sizes right now. So I will go back and say pick again, add rectangular. Now my beam size is 9 inch by 18, made up of concrete 3, depth is 18, width is 9, reinforcement, it's a beam 1.75 and 1.75. So second size is also defined. Again, beam 12 inch by 15 inch, concrete, depth is 15 inch, width is 12 inch. Go to reinforcement, beam 1.75, 1.75, press OK, press OK, and that defines my third beam. Then I go ahead and define my last beam, which is beam BM 12 inch by 18 inches, made up of concrete 3, 18 inches depth, width is 12 inches, and then it's beam 1.75 and 1.75. Press OK and OK. So that defines my 4 beams, and you can define as many beams as you want. Okay, everybody's clear about this? Now we can define some columns. Always remember that the minimum size of column which generally structural engineers follow is 12 inches. Nobody I have seen go below 12 inches. And in some exceptions, it may be 9 inches. But generally, because 9 inches is too small to accommodate steel bars and to do the compaction. You know, when you are casting a column, say it is 12 feet high column, you have to insert the vibrator inside the column. So 9 inches, it's too small. Generally, people don't do that. In one case, I remember there is a hospital in Rawalpindi, Fauji Foundation Hospital. Fauji Foundation is a big hospital. I was designing it long time ago, and they had a requirement that we want all the columns flush with the walls. They didn't want to see any column projected out of the wall. So they restricted the sizes to 9 inches. And then the column sizes were 9 by 36 inches, 9 by 48 inches. So it was more of a wall than a column. It was the time when we had an earthquake in 2005. So we submitted the first design on zone 3, and then earthquake came. And then we had to revise our design completely on zone 4. Although Rawalpindi is not in zone 4, but still they wanted that it's a hospital, it's an essential facility, so we want some higher zone consideration. So that's why the sizes were too big. More of a column, more of a wall than a column. But except that, I never have experienced that somebody used 9-inch thick column. So remember, as a general rule, that minimum size or minimum dimension of column which is practically used is 12 inches. 15-inch is a desirable size, or it's a good size. So generally our sizes, when it is rectangle, when it is square, start from 12 inch by 12 inch, 15 by 15, 18 by 18, 21 by 21 in multiple of 3 inches. But it's not the case that you always have square columns. You can also have rectangular columns. Okay, so even in rectangular column, you move in the size of 3 inch. Say 12 inch by 15 inches, 15 inch by 18 inches, or 18 inches by 21 inches, sometimes 15 inches by 21 inches. There is no universal rule, but you will learn this thing when you will practically design structures. The thing is that the way you learn it, when you go to the design office as a fresh structural engineer, you study their previous designs. Their drawing sets are available from the previous project. So first thing you should do is you should ask for the drawings of previous projects. So from the previous designs, you note down these basic things, that what sizes they are using, and what is the format of the drafting, and other things, and how they write the general notes and other stuff. So you will learn that what is the practice of this company, and then you can follow the same practice. So I shall define 3 column sizes here, starting from 12-inch square, then 15-inch square, and then 18 inches square, just to demonstrate you. And that will be done right here in the same panel. Add rectangular. This time I will call it column 12 by 12, made up of concrete 3000. The size is 12 inches by 12 inches. And I shall also define a rectangular column for your understanding. And then again you go to the reinforcement and now say, okay, it's a column, right? And it is a rectangular column, it's not a circular column. And if it is a rectangular column, it has ties. Okay. I will jump to the bottom right here. You want to check the design, or you want to check the capacity, or you want to design the column. Look, there are 2 things. One thing is that you tell the software that what is the magnitude of reinforcement in this column. You tell the software that you have these many bars in one direction and these many bars in the other direction, and these are the sizes, and once ETABS has this information, it can check the capacity. it can tell you that whether this size and this reinforcement together meet the capacity requirement of this column. And what is the demand? Demand comes from structural analysis. It will do the structural analysis, find out that what axial load and bending moment this beam has to bear, and then correspondingly calculates the capacity and tells you, okay, the capacity is this and load is this, so whether it satisfies or not. This is one way. The other way which we will follow is reinforcement to be designed. We are just telling the software the size. The size is 12 inch by 12 inch. Now software tell us that for the loading, what reinforcement do we need. So when you design a new structure, then you use this option. Sometimes structural engineer has to check an existing design. A building is already constructed, and we do this thing in our department very frequently, especially whenever there is an earthquake or when the purpose of the building has to be changed. It was an office building, now they want to convert it to warehouse, the loading is higher, or there is any other damage, or the age of the building is more, so they want the capacity analysis. So we have existing drawings. We put the reinforcement and sizes from the existing drawing in our software, and software tells us whether this is safe or not. So when you have an existing drawing, existing design to be checked, you use the first option. But when you are designing a structure from ab initio, you use the second option, and we shall use the second option. So if you are using the second option, then this information is immaterial. Okay, you check this one and this, no problem. So reinforcement to be designed. You don't have to worry about the bars. Now I define 15 inches by 15 inches made up of concrete, 15 by 15. This is correct. This is correct. Everything is by default correct. Yes, you can, if you are little, you can add this cover to rebar center. That you may need to add. You can add this. Let's add the same value as we did it for the beam. It may be different for the columns, but I will go ahead and add the same value here. You can check ACI code. The ACI code may have different concrete cover for column and for beam, but I am plugging 1.75. Column 18 by 18 made up of concrete, 18 by 18, and the rest is same, and I change this 1.75. This right now this is FPS, you see, but you look, start from number 2 and goes to number 18, but you have matrix sizes as well. For example, number 10, 15, 20. As I told you that there are different designations from different parts of the world, but don't worry about the size right now, because we are designing the column, the size won't matter. Okay, now I will add a rectangular column, column 15 inches by 18 inches. Okay, now here is a catch here. You need, in your real structure, this is a plan. Say you have a square column here, okay, and you have a rectangular column here. This is a rectangular column. Okay. You have a rectangular column here as well. This column, say this column, this dimension is 18 inches and this dimension is 15 inches. And same is here, 15 inches and 18 inches. Both the dimensions are same, but their orientation is different. In ETABS, these are two different columns. You can't use the same section for these two column shapes or these two column sizes. Although sizes are same, but orientation is different. There are two ways to doing it. The easier way is that you define two sizes. One 15 by 18 and other 18 by 15. Now the question is how you will know what is depth and what is the width. Okay, that you can define and see by yourself. That you define it and install it and look at the orientation. If the orientation is right, fine. Otherwise, delete that column and insert the other one, and you will see. Okay, now it looks fine. Other option is first option is define two sizes. Fine. Other option is define just one size. Okay. And there is an option in ETABS that you can rotate the section. So install the section. If the orientation is accordingly, fine. You can just leave it like that. If the orientation is different, then you can rotate the section at 90 degrees, and you will get your required orientation. Right? Understand? Two ways. Either define two sizes or define one size, and whenever you need, rotate its orientation in your chart. As a beginner, you can define two sizes. So it's 15 inches by 18 inches. Now, right here, it says depth and it says T3 and it says width and it says T2. This 2 and 3 are actually these axes, 2 and 3. Okay. There is a global axis system which is X, Y, and Z. This is global axis system. There is another axis system which is called local axis system, and that is 1, 2, and 3. What you see here, 2 and 3 is local axis. Remember, a universal truth for the software, that 1 is always longitudinal axis for a line element, of course. For a line element means for a beam, for a column, for a truss member, for a light pole, for anything which is a line member, which ETABS calls a frame. 1 is always a longitudinal axis. So what you see here, you see two cross-sectional axes. What are they? 2 and 3. 2 and 3 are in the cross-section. 1 is not visible, that is in the depth, which is the length of the member. Everybody clear about this? Yes. 1 is always a longitudinal axis. For example, this beam, 1 is longitudinal, axial. Okay? 2 and 3 are like this. 2 and 3 may be vertical. I'm not sure. For a column, this axis is 1. Okay. Now notice the change in dimension. For example, right here, you don't know what is T3. You don't know whether T3 means the dimension parallel to axis number 3, which is this one, or it is perpendicular to axis number 3. You don't know, right? So you need to change something. For example, I am changing T3. I am making it 24, and see what dimension changes. Now tell me, T3 is what dimension?
Parallel to axis.
T3 is perpendicular to axis number 3. Axis 3 is horizontal, and right now it's vertical. I mean, I shouldn't say horizontal or vertical, but I make it 50 inches like this. So we find out that T3 means the dimension which is perpendicular to axis number 3. Okay. So in this column, this one, this column versus this column, or if I use the notation which that section has, if this is 2, this is 3, this is 2, this is 3, right? This is 18 inches and this is 15 inches, this is 15 inches and this is 18 inches, right? So in this case, T3 is 15 inches and T2 is 18 inches, right? And for this one, T3 is 18 inches and T2 is 15 inches, right? So you need to define 2 of them. A common practice is that generally the bigger dimension is called depth, although it's not a universal truth, right? For example, ETABS call T3 as depth. Look at ETABS. ETAB calls T3 as depth. If you have something like this, then in this case, what we have right now, T3 is smaller and T2 is larger. But in the language of ETABS, 12 inches is the depth and 24 inches is the width. So you need to understand, these are the things which are specific to a particular software. So you need to learn what is the notation of a particular software. It may be different in STAD or may be different in other softwares. Okay, so I am defining 15 inches by 18 inches, just making T3 18 inches and making this as 15 inches. Okay, so in my case, what I have defined is this one, what you see from there, right? T3 is 18 and T2 is 15. Just need to change the cover. Press OK. Okay, so I finished this define frame section. So we have spent ample time on defining frame sections. So you can have a list of frame sections already defined, so that when you are designing your structure, you don't have to go back and define sections. You can just pick those sections and use them right away. The next thing is slab. I'll finish at 2:30, 2:35. Okay, we are defining slab. By default, you have deck, flank, slab, and wall. Flank is something which has smaller width and longer length. Wooden planks. Have you seen wooden planks? Yes. Okay, that's here. Wall, slab, deck section. In the bridges, we call the slab as deck. And sometime in steel structure, the steel platform is also called deck. So that terminology is not generally used in reinforced concrete buildings. In RC buildings, we use the term slab. Flank is something different, like a wooden plank, smaller width and more length. Wall is, of course, wall, shear wall or a retaining wall. I will define both of them for you here. So you can come here and say add new slab. When you add new slab, you have this thing here. First of all, name. My slab is 6 inches thick, so I will call it slab 6. My slab is made up of concrete 3. Okay. And here are two options: thickness, membrane thickness, and bending thickness. What does that mean? You remember corrugated sheet from steel? Yes. That looks like this. Yes. Okay. In this case, the thickness of the sheet itself, this thickness, is membrane thickness. Okay, the membrane, and the overall thickness, this thickness, is bending thickness. So in a corrugated sheet, membrane thickness is different and bending thickness is different. Right?
But sir, slab में तो same ही होती है.
This is a corrugated sheet, right? But our slab, concrete slab, is like this. A concrete slab, say 6 inches. So you can see that in case of a concrete slab, there is no difference between membrane thickness and bending thickness, right? So we will plug same value for those two cells. So in our case, bending thickness and membrane thickness both will be 6 inches. 6 inches and 6 inches. Now there are three options: shell, membrane, and plate. Okay, you don't know the structural difference between these three things. It's a part of your structural engineering course, but I can briefly tell you. In reality, if you look at the behavior of slab, it should be defined as a shell element. Okay? It should be defined as a shell element. Okay. I don't have an example of shell, but this slab has a bending stiffness. If you try to bend it, you can easily bend it. It resists bending. Why it resists bending? Because you have a mesh of steel bars, longitudinal bars. Those steel bars helps concrete in resisting bending movement. So the slabs resist bending moment. It also resists shear force, right? So in theory and in practice, or in real life, I should say, the slab should be modeled as shell. Okay, but generally, when your structures are large, these shell elements consume so much memory to solve that we do not model the slab as a shell element and do an approximation. If your structure is small, 2-story, 3-story, that's fine. You can model it as a shell and that will be close to reality. But in multi-story buildings, shell elements consume so much memory that your model may take hours to analyze unless you have a very good machine. So we do not use shell and deviate from reality and use membrane element. Okay. I should use membrane element. What is a membrane? This is a membrane. This membrane has no bending stiffness. What do you mean by no bending stiffness? Or minimum bending stiffness means you apply a small load and it will bend, or even it will bend under its own self-weight. No bending stiffness, right? It has no shear stiffness. Very small, right? Does it have any stiffness?
Little. Tensile.
It has non-exit. It has only tensile stiffness. In compression, it crumbles, right? But in tension, no, it is strong. You have to apply a force to break it, right? You don't need any force to bend it, to slide it, to compress it. But when it comes to tension, it has stiffness. This behavior is called membrane behavior, right? But our slab in reality is not a membrane, right? But we shall model it as a membrane. It means we are underestimating our structure, right? We are eliminating the stiffness of our structural member, but because of memory limitation, we have to do it. Now, what will slab do, or what will be the role of our slab when we shall model it as a membrane? It will only transfer the load to the beams and column. We model it as a membrane and apply the live load and dead loads on the slab, which is a membrane. So what ETABS will do, ETAB will distribute it according to tributary areas. You remember those triangles and trapezoids? So it will calculate those areas and multiply the intensity of loading with that area and transfer it to the beams, and then beams transfer it to the columns. So if you model your slab as a membrane, then the only role of that slab is just to help the software in calculation of tributary area and transfer the load to the beams and the columns. It has no structural contribution towards the structure, no addition to the stiffness or strength of our structure, which is underestimating our structure, right? But we are on the safer side. So for large size buildings, for multiple story buildings, and when your machine is not very good, you use membrane option. But in reality, it is a shell element. In newer version, you may find an option of thick plate and thin plate. The difference between shell and plate is related to shear stiffness, but that is more theoretical, and for practical, in plate it also considers the deformation due to shear. In our regular buildings, when we calculate deflection, we only consider bending moment. If you recall moment area method or double integration method, you always use the moment to calculate the deflection. You never considered shear to calculate deflection, although shear will also cause some deflection. We call it shear deformation. But in practical life, you don't need to go into that depth. So we ignore the shear deformation. We only rely on or only consider the bending deflections. So that's the difference between plate and the shell. One considers the shear deformation, the other doesn't. But we don't have to do it for our buildings. So we shall either use shell element or membrane element. For smaller structure, we use shell, and for bigger structure, we can use membrane. Right? So right now, I will pick membrane. Okay? So you can pick membrane. That's all you need to do on this one. Press OK, and you will have slab 6 in your list. Yeah, power back. Okay, I will also define another slab which is 5 inches thick. Slab 5, made up of concrete, 5-inch thick, 5-inch thick, and I am taking it as membrane. Press OK. And now I shall also define a wall, considering that I may have a shear wall. Okay, so I can generally the wall sizes start from 9 inches. Maybe somebody use 8 inches, but when it comes to shear walls, lift well, 9 inch is a very decent size and commonly used, and maybe 12 inches. Okay, I'm talking about medium-sized buildings like 10-story building or something. But for high-rise buildings, you know, super tall buildings is completely different. So my wall is 9 inches thick, made up of concrete 3, has 9 inch and 9 inch. 9 inch. Now here is something you need to remember. You can never model a wall as membrane. You have to model it as a shell, because role of the wall is completely different. In case of slab, the role of the slab here, when you define it as a membrane, it will calculate the load and transfer it to the beams. But the main objective of the wall is to resist the lateral movement under the earthquake or for the wind. So if you model it as a membrane which has no stiffness, then practically it is ineffective. There is no use of installing a wall which has no stiffness. So wall, or I should say a lift well or a shear wall, will always be modeled as a shell element. Okay, always shell element. For the older version, you have only shell. For the newer version, you may have thick shell and thin shell. That's a plate actually. There are small differences, but you can right now make it thin shell. But in your notes, make a question mark, and I would say go to the manual of the software. And read about shell, thick and thin, membrane, and plate. Okay. So you may have some good information, and the help should be right here. Help, search help, documentation and tutorials. If you are interested, you can go to the documentation. Find out, you may have to spend time on this. This is modifier. This is maybe how to define it. Yeah. Look, shell type behavior. Shell type behavior means that both in plane membrane stiffness and out of plane plate bending stiffness are provided by the section. Look, this is in plane, this is out of the plane, right?
Yes, sir.
So in case of shell, you have both in plane and out of plane. In case of membrane type behavior means that only in plane membrane stiffness is provided. Only in plane, right? Plate type behavior means that only out of plate bending stiffness is provided for the section. So it means that plate is in between shell and membrane, right? Shell has both in plane and out of plane. Membrane is in plane and plate is only out of plane. But it also talks about shearing deformation. That's what I was talking, but you can read it later on. It talks about out of plane shearing deformation, which is more sophistication. But I strongly recommend that you shouldn't just remember that which option we have to pick. You should know why we are picking one option and leaving the other one, and that you can find out from the help. So you shouldn't have just a surface knowledge or a two-dimensional knowledge what I show you on the screen, but you should add the third dimension to the knowledge. I mean, you should go in the depth. Depth is the third dimension which you can find from the help or from the tutorials or other stuff. Okay, and a lot of stuff is there on the internet, but this is a very good resource. All the options are explained. Which option means what are explained here in the help. So I strongly recommend that you should jump to the help whenever you need to pick an option. Pick an option. Okay. So we define material. Okay, just a minute. Material, frame section, and slab section.
Yes. Next, load combinations.
Next is load cases or load patterns. Right? We will stop after this one, but I want to finish this one. In the newer version, you go to load pattern. In the older version, you go to load cases. Okay. Actually, load pattern or load cases are basically types of load which you think your structure will be subjected to. Okay. For example, this load is occupancy load. You yourself and this furniture. We call this occupancy load as live load. Live load is the load which can change its magnitude and position, right? Sometimes it is less, sometimes it is more, sometimes it is completely absent, sometimes its magnitude is less and sometimes magnitude is more, and position is also different. That's live load. Dead load is what? Dead load is self weight, which is inherent weight, and the other dead load is superimposed. What is superimposed? Floor finishes, roof details. These are superimposed dead load, or anything which is permanently attached to the structure and you think that it's not going anywhere throughout the life. You can call it a superimposed dead load. But either superimposed or other one, it's a dead load. Okay. Remember that the software calculates the self weight of the members by itself. You do not have to calculate the self weight and apply by yourself. No. You define only the sections, that my section is 9 inches by 18 inches, my column is 15 inches by 15 inches. It will count the number of columns, count the number of beams, and from the area, from the dimensions, it has all the dimensions, length and cross section, and it has density of the concrete, so it will calculate the self weight. Okay, so do not worry about self weight. There is only one option which will do, and it will calculate self weight by itself. You have to worry about the live load. You have to worry about the superimposed dead loads, and you also have to worry about wind loading and earthquake loading. Right now, we will not go into earthquake loading. Maybe after the mid semester, you may have studied the earthquake loading. Then we shall define earthquake loading and also the wind loading. Wind loading you may have already defined. You know it from your steel structure. When you have a wind velocity and windward side and leeward side, there are coefficients that you may do. But let's stick to the basics right now. If you look at here, it already has live load and dead load. Let me try to delete them. You can delete only one of them. The last one you can delete. This is name and this is type. You can name it anything. Name doesn't define what it is. Type defines what it is. Okay. So you will find dead, super dead, live, reduced live, notional. Notional is generally used for bridges. Quake is earthquake, wind is wind, and snow, and others in case. So we shall define dead, live. Okay, reduced live is generally used for high-rise building or when the area is very large. When the area is very large, then the chances that the entire area would be fully loaded with live load all the time is very low. So what you do, you reduce it a little bit. You actually learned it in your steel structure, but I'm not sure if you still remember it. So what we do, instead of saying that the entire area would be loaded, we reduce it maybe 85% or 90%, maybe 75%, and we call it reduced live load. There is a formula which is used to reduce the live load, but for smaller structures you can continue with the live load, don't reduce it. And we shall define quake, earthquake, and wind. So right now let's talk about dead. As I told you that you don't have to worry about the self weight. Other than self weight, there can be floor finishes, there can be roof details which are different, there can be partition load, 4.5-inch walls. You can define all those separately here. For example, I define, what is that? Floor finishes, FF, okay? Type, FF, and because this dead load is already defined, I am just changing the name, so I will say modify the load. When I modify the load, it will change the name to FF. FF is floor finishes. it is dead load, and yes, self-weight multiplier. Let me talk about this in a minute. I am going to define another dead load, which is my roof details. Now I will do add new load. Okay. Here is the thing, very important. This is self-weight multiplier. Self-weight multiplier means that if this value is 1, then it will include the self-weight, right? If the value is 0, it will not include the self-weight. You can make it 0.5 and it include half the self-weight. You make it 3, it will reduce 3 times. But here is something which you need to learn. But before that, I define partition load, PL, partition, and say add new load. Now see, how many dead loads we have? We have 3 dead loads, and all of them have self-weight multiplier equals to 1, which means that ETABS will add the self-weight, calculate the self-weight, and add the self-weight to all of them. So it means right now, according to our definitions, self-weight will be considered 3 times. We have to make it 1 time. Okay. So for that, what we need to do is pick any of the 2, say this one, and make 0. Modify the load. Pick this one, make 0, and modify the load. So now you have what? Now you have 3 dead loads, fine, but only one of them has self-weight multiplier equal to 1, which means that self-weight now will be considered only once. So you need to have self-weight multiplier 1 only with one of the dead loads. Okay? With the live load, you never think about self-weight. With the earthquake, you never think about self-weight. It's only one with one of the dead loads. Okay. Now I define live load and name it live, and simply say add new load. You don't have to categorize live load in general, but maybe in some specific cases you may need to do that. Maybe you would, ASC, American Society of Civil Engineers, that provides you a guideline about approximate live loads for different buildings. For a classroom it's different, for a hospital it's different, for a corridor it's different, for a warehouse it's different, right? So you can use those values, but all of them are actually live loads. The generic is live, so you don't have to define multiple live loads. And it includes furniture, not just human beings. For example, if the load for the classroom is a specific number, say 60 pounds per square feet, it includes human beings and furniture and fixtures, whatever it is. So I am skipping, you can write in your notes that right now we are skipping the earthquake and wind. And we will come back to this later on at some point. If I forget, remind me after 2 months. I mean after the mid-semester. So with this we have finished the load cases. Tomorrow, not tomorrow, Thursday. Thursday we will start from load combinations. Okay? Okay. That finishes the lecture. Last time I asked you to make groups, and I said that I want that there has to be a group of 5 students, and each group has a leader. So group leader will give me on a piece of paper his name with his GPA and name of 4 members. Right? That's what I said. So the group leader can be any person. There has to be 5 persons in a group. Anyone can be the leader. but I just need the GP of the leader. Okay? CGPA. CGPA. Yes, CGPA doesn't matter, you are right. It's just for project allocation. Okay, so is everybody ready?
Yes.
Who is the group leader? Who are the group leaders?
Where is my group?
Okay, listen to me. I am talking to you. Okay. Now,